All right, so welcome back. We're going to do 3.3 today, which is logarithms. I know right now I can't even spell logarithm. It's okay, I can't either. But we're gonna get this to work. All right. So the biggest question that probably people have when they start logarithms is, what the heck is it? And I remember being young and having people, asking that very same question. I just remember doing flashcards, and I saw the square root symbol, and I said, "What's that?" And I said, "Never mind. You do learn the addition first, then we'll talk." Okay. So, and then we did logarithms, and I said, "What is it?" It's an exponent. Like I was doing, the table, the flashcards for plus and minus, so that was not really a very effective answer. But it was correct. It was kind of a snarky answer, but that's okay. And I'm going to tell you that's pretty much what the same thing is. It's like, well, what's a logarithm? It's an exponent. Like, what do I mean by that? So we have the notation we use is log, and there's a base b here. Okay, so this is log base b, log base b. Okay, of x is equal to y. Okay, so that's how we say. And this b here, this is the same b as base. Okay, so this is the same b as this b is the exponential b. So we did exponential functions, and we said, okay, well, b to the x, right, is equal to y, and we had some conditions on this, right? We said, well, b has to be at least positive, and b can't be 1 because that would be kind of silly. So the same rules apply because this b and this b are the same b. Okay, so this b has to be positive, and it can't be 1. Right? So please forgive this because this was, logarithms are 1600s, so we're looking at 17th century technology here. So the way they read this, and this is what's weird, is because the people of the 17th century spoke and thought a little different than we do. So this is b to the y is equal to the x. Okay. So the answer for a logarithm is, what exponent do we have to raise y to in order to get x? Okay. So what we have is something called equivalent exponential form. And we're saying that b to the y is equal to x, right? So when they say, well, what's a logarithm? And they respond, it's an exponent. What they're referring to is the answer you get, right, is the number that's an exponent. It's what number do we have to raise b to in order to get to x, okay, to get to the argument. And I know that's kind of a weird way of saying it, but I want you to, when somebody says, oh, you say, we studied logarithms. Logarithms, what's that? It's an exponent. Okay, so I want you to remember that because that's exactly what it is, but it's kind of an exponent, but in a roundabout way. It's not quite as hard as what it seems like. I mean, it is, but it doesn't have to be. So with log base 10, right? So it's x is equal to y. So the exponential form is 10 to the y is equal to x, right? So if I ask you, like, what's the log base 10 of 100? Okay, what we're asking to is 10 raised to what number? Actually, move over a little bit. Look at the end here. Okay, so 10 raised to what number is equal to 100? All right, and that answer would be 2, right? 10 raised to the second power. Excuse me, I'm going to sneeze again. Allergies. All right. So 10 raised to the second power is 100. Great. Log base 10 of 1,000 is equal to what? We're going to say 10 raised to what number is 1,000? Right? And 10 times 10 times 10, right? 10 cubed is going to be 1,000. So this is going to be 3. Right? 10 raised to 10,000. And we're going to say 10 raised to what power is 10,000. I hope you're noticing a pattern here. 1, 2, 3, 4 zeros, and 10 to the 4th. Okay, so when they're really easy numbers, we have log base 10, then the answer tends to be really easy. Okay, it's just count the zeros and you're set. Now, for 200, it's going to be a different value. Okay, for 300, it's going to be a different value. It's going to be 2 point something, right? For 3,000, it's going to be 3 point something, but it's like we're not going to be able to predict that very well. But for nice and easy ones, you're going to say, okay, this is what we're going to do. Why would we want to do this? Well, this is supposed to make our lives easier, okay? And in sciences, there's graphs, right? Where maybe we want to graph like the different sizes of the different weights, rather, of different mammals. Maybe we're trying to figure out like brain size, or maybe we're weighing offspring. We're comparing the masses of different animals, and we want to see like, well, how many calories a day do they take to be alive? How long do they live? Something. But maybe we are interested in their masses. Well, we got to deal with everything from like mice and shrews, right, up to, large mammals, like, humans, compared to mice, we're very large animals, but large compared to us, right? There's rhinoceros, right? There's elephants, and we're comparing all of the masses. Like, well, how much does a mouse weigh, right? And that they're, maybe a couple 100 grams, right? Maybe 300 grams, maybe 500 grams. I know squirrels are like 500 grams. Humans, well, healthy ones anyway. Right. Let's see. If you had 100 kilograms, that's about 200 pounds. So we have up to 100 kilograms. So I'm going to go ahead and I'm going to write down 100 grams. I need 1,000 grams in order to get to a kilogram. So I got to go 100 grams, 200, 300, 400, 500, all the way up to 1,000. We'll do 1,000 grams, and that's 1 kilogram, right? 1,000 grams is a kilogram. So we're going to keep going so we get to 100 of those, right? And then elephants, those weigh several hundred kilograms. So I think it was a ton. What, 2,000 pounds? So we need about 1,000 kilograms in order to get to a ton. So we're going to go from 100 kilograms to 1,000 kilograms, and we're going to put this on a graph. Right? No, that's not happening. We're not going to go ahead and do that. So we use what they call a logarithmic graph. Okay. So what we might do is, I don't know what's going to be on the y-axis. It's whatever we're interested in studying, right? But if this is in grams, we might have, we have a 1 here. We're going to say, well, this is going to be 1 kilogram. 2, that's going to be 100 kilograms, or 100 grams rather. 3 is going to be 1,000 kilograms, or 1,000 grams. So 4 is going to be 10,000 grams, etc. Okay. So rather than have this graph that's longer than your arm on one piece of paper, we're going to have one graph that just pretty much counts 1, 2, 3, 4, and it's just the zeros that are behind this. It's called a logarithmic scale. Okay, and it's very useful. It happens a lot in sciences. I mean, if you look at astronomy, right? Astronomy. Look at astronomy. The distances between things in space is immense. And if you had to make a regular graph for that, that would, you die of old age by the time you got done making that graph. So we need something better, and this is better. Okay, I think the Scoville scale for how hot chilies are is, it's an exponential scale. It's you're going to need a logarithmic graph to kind of track that. So you don't want to put in how hot a regular bell pepper is on the same graph as, like, ghost peppers. They are, again, you do a linear scale, you're going to be here for a long, long time writing out all this graph stuff. You don't want to do it. So it's easier to see if we just count the zeros and we don't worry about that. So despite, all the difficulty and all the problems that we have, all the stuff that we do here, it's all kind of designed to make your lives easier in some way or another. So hopefully you guys hopefully you'll take classes where you get to see that, but that's what we have. All right, so let's do a couple other little issues here with logarithms. There's really, despite what math books will tell you, there's 3 logarithms. Okay, 3 logarithm bases anyway. We have base 10. That's the most common log there is. We use 10 when we're not interested in how things are changing. We just want to put things, on a scale. Since humans have a base 10 number system, or at least, our modern society uses base 10 number system, it's best to more or less use this one. Okay, every time we have a placeholder, right, it's at 10. So there's 10, 100, 1,000. Okay. We use base 2. As I said, in our modern world, for humans, it's easier for us to think in base 10 because that's how we do. But computers don't think in base 10. Computers think in base 2. So if you're a computer engineer, you're a software engineer, you're testing out how long it takes for a program to do something, generally they like to do log base 2. Okay, and that would be, actually, hold on, this. Oops, I wanted to erase. I didn't want that. Okay. And it is so common, in fact, that if you just see LOG without any base on it, you should, that means it's base 10. Okay, so if you have log x, we're going to be assuming that's base 10. If it's 2, then your calculator does not have this. Okay, some calculators might, but most don't. But again, if you're going to be a software engineer, you're going to use LG, okay, which is log base 2. Okay, so that would be log base 2. This would be log base 10. Okay. And then if you are if you're studying a science that really cares about how things are changing, okay, we use a log base E. Okay, so we use log base E, and that has a special sign called ln x. Okay, so this means the natural log. Okay, log is called the common log. Okay, most people, when they say log, they usually mean this. Okay, however, if you're going to be studying physics, if you're going to be studying math, if you're going to be studying finance, those sciences really care about what is the change going on. So they use natural log because when you do calculus with natural logs, with base e's, you don't have to have any scaling factors. Log base 10s, we have to add in scaling factors, and they're usually based on E anyway, or natural log anyway, so it's just easier to use a function that does not have a scaling factor that goes along with it. Okay. Now, math books will have you believe that we can use logs of any base, and technically we can, but the only time you're going to see like log base 6 is going to be in a math class. So I'm giving you permission. I'm saying, like, look, if you don't quite get this, like, that's okay. It's not going to be the end of the world. There is going to be one question on exam of like a weird base that you don't have to deal with, but that's one question out of 9, or it's one question out of 10. So you will definitely suffer a little bit, but honestly, it isn't the end of the world. Okay, if you get everything else, if you're like, I am brilliant with natural logs, and I'm brilliant with log base 10, I can do common logs. By the way, we still teach to the 20th century, so no math book, we don't really use this yet. Okay, this is very, very specialized, but it's getting more common. Okay, so you'll see this one too. But yeah, I say, oh, I mastered this and I mastered this, but logs of like 6 or 7, they just throw me. Like you're going to do a little bit less than if you had gotten them, but Yeah, it's not the end of the world if you don't do those. But here's how you untangle them. Okay, is we're going to say, log base something. Let's pick log base 3 of x. We're going to write this in the equivalent exponential form, and that's how we're going to unravel this. Okay, so we have log base 3 of x is equal to y, and I don't want to say equals. I just want to say the equivalent form. Okay, is b to the y is equal to x. And if you have like a hint of thinking, wow, this kind of reminds me of inverse functions, then you would be correct, which is why we put inverse functions in chapter 3 just before you get to logarithms, so that it feels like they're connected. Because exactly, I don't want you to say, oh, this is an inverse function and this is exactly how they're related, but I do want you to look at this sort of relationship and think, well, this reminds me of inverse functions. Yeah, it tastes like an inverse function. Because that's what we're doing. And that's exactly how we're going to sort this out. So if I ask you, like, what is, say, log, let's go with a 4/3 of x is equal to y. And I wanted to graph this thing. Well, what I'm going to do is I'm going to say, well, that's going to be 4/3 raised to the y is equal to x. So that's kind of crazy. I'll agree, it is kind of crazy. By the way, there is, I know of one equation, and they really went out of their way to do this, that used both a log base e and a log base 10 in the same equation. I have no idea why they did that, except like maybe it was two equations coming from two different areas to do this. But if you see two different bases for your logs, like you should really look at that person and like shake them until they stop moving, because like, what are you doing? Okay, honestly, what are you doing? So what we're going to do is we're going to pick y's. Okay, so that this works. I still remember that formula. I'm like, you have to memorize this. I'm like, I am not memorizing a formula with two logs in it. It's not happening. So what we're going to do is we're going to pick our y's. Okay, so our first step is write in equivalent exponential form, because that's the only way we're unraveling this. Okay, our second step is we're going to pick our y values here. Okay, so we're going to pick y values. All right, and now we're going to use the form, right? We're going to use our equivalent exponential form to generate the x values so we can graph. All right, so let's go with 0, right? 4/3 to the 0 is 1. Right? 4/3 to the 0 power is equal to 1. How about 4/3 to the first power? Right, that's 4/3. 4/3 to the second power? Right, that's going to be 16/9. Right, square the 4, square the 3. If we do the negative 1, right, 4/3 to the negative 1, that's going to give us 3/4, right, because negative 1 means reciprocal, so we have 3/4 here. And then 4/3 to the negative 2, we'll do over here, 4/3 to the negative 2, right, is reciprocal, but it's 9/16. Okay. Unlike exponential functions, logarithms, you can do a fairly large base with a logarithm and get away with how that's going to work. So I could have used 3, and I probably should have. Well, maybe that's the next example. But yeah, they are of less trouble to deal with than exponential functions. Okay, so let's go ahead and graph. All right. Notice, though, I want you to notice, let's look at my x values. they're all positive. Okay? The domain for a logarithm is just the positive powers of x. Okay, the positive values of x rather. So this is going to take place in quadrant 1 and quadrant 4. Okay, our domain is going to be 0 off to infinity. Okay, because we can pick any of these numbers. Our y values, though, are going to be plus and minus. Okay, so the range, right, everything is negative infinity, positive infinity. Okay, positive infinity, it's a logarithm. It doesn't go very fast, right? 100 would be 2. 1,000 would be 3. Like I know, but we could have, 10 to the 1,000 to the 1,000 kind of numbers, and eventually it'll go big. But it's just going to take its sweet time getting there. So we have a value at 1, 0. Okay. And so that's this one. Then we have 4/3. Okay, let's go here. Let's say this is 2. So here's 1, here's 2. 4/3 is about here, right? And that's a value of 1. And then 16/9. What is 16/9 exactly? So this is 16. Oh, yeah, 16/9. I just want to know that. 1.8. Okay. So here's 1.8, and we're at a value of 2. Okay. And then let's see here. We have 3/4, right, 3/4. So about here, down here, and then 9/16. 9/16 is a little bit bigger than 8/16. 8/16 is here. It's half, so it's a little bit smaller than that, a little bit bigger than that rather. We're down here at -2. Okay. And that is the shape, right, of every logarithm graph you're ever going to encounter, more or less. All right, and just like exponential functions, we can move this around, up, down, sideways. We could do, log of -x and flip it. We could do negative log of x and flip it. So there's more than one way to do that. But there's all sorts of shenanigans we could pull with, like where this graph is and stretching it out or pulling it together or whatever. Okay. Let's do 3 in a second here. What do we have? We have, oh, that'll be good. We have an asymptote, right? We have a vertical asymptote. X equals 0. Okay, so there's a line here that we cannot cross, right? Vertical asymptotes, can't cross those. Those are absolutes. Horizontal asymptotes are more like guidelines, but, there we go. Okay, so let's try 3. Let's try log base 3 of x is equal to y. Remember, it's an exponent. So the way we're thinking is 3 raised to the y power is equal to x, right? Or equivalent exponential form, 3, the base, right? The reason why I want you to remember, like when you tell somebody to be kind of snarky about it and say, that's an exponent, because 3 to the y, right? The exponent, the answer is the exponent is equal to x, and this is the argument. Okay, so we have the base raised to the exponent is equal to the argument. Okay, this, just memorizing this form is going to help you in figuring out, like, did I ever do that? Okay, is going to be is going to help us figure out how this is going to work. Okay, so really need to get that done. So our first step, right? Write an equivalent exponential form. Okay. Our second step is we're going to choose our y's. And choosing the y's is going to be the same thing over and over and over again, right? Just like x, when you build these tables, right? You always build -2, -1, 0, 1, and 2. Okay, so we're just going to follow that through. You can pick other numbers, but these are nice. 3 is we're going to figure out, we're going to use our equivalent exponential form to generate our x values. Okay, so there we go. So we're going to say 3 to the 0 is equal to 1. By the way, a logarithm is always going to cross. I mean, if we don't mess with it and do a vertical or horizontal shift, a logarithm is always going to cross through this point. All right. 3 to the 1, right? 3 to the first power is going to be 3. So when x is 3, y is 1. 3 squared, that's 9. So we have 9. When x is 9, y is 2. Okay, we have 3 to the negative 1 is 1/3. Okay. And 3 to the negative 2 is 1/9. All right, there we go. So now it's time to graph. So let's go with 1, 2, 3, 4, 5, 6, 7, 8, 7, and there was 9. So 3, 6, 9. Okay, so we have a point here at 1, 0. So we have this point. When x was 3, right, y is equal to 1. Okay. When x is 9, right, we're all the way up here at 2. So yippee. Okay, we have x to being 1/3, so we're here. Okay, give or take. And we were at negative 1. Let's see, what was it? And 1/3 of 1/3, so let's maybe in here somewhere. We're down here at negative 2. Okay, and again, it's pretty much the same shape as we had up here. Okay, there's more of a bend to it because we have a bigger base, but that, yeah, that's what we deal with. But that's pretty much the graph of this thing. Really show us one more. Okay, and we're going to do y is equal to log of 1/3 of x. Okay, so this is the first time our base has been less than 1. Okay, the first time it was 4/3, bigger than 1. Second one is 3, bigger than 1. This one's 1/3, less than 1. And let's see what happens to the graph. So our equivalent exponential form, right? 1/3 raised to the y is equal to x. Okay. Good deal. Okay. So 1, right? Translate to equivalent exponential form. 2, we're going to pick y values. Right, so we're going to make our little t-table here. And our y values again, right? My goal, by the way, is at the end of this little section, you're going to say, oh, logarithms, they were so boring. They were too easy. I would love for you to say that. So picked our y values, and then we're going to use our equivalent exponential form to get x's. Okay. So here, 1/3 raised to the, right, 1/3 raised to the 0, it's always 1. Okay, 1/3 raised to the 0 is 1. Oops, come on, erase. All right, 1/3 raised to the 1 is 1/3. 1/3 raised to the 2 is 1/9. Okay, to the negative 1, that was going to be 3, right? 1/3 raised to the negative 1 is 3. 1/3 raised to the -2 is reciprocal, so it's 3 squared is 9. All right, so I just want you to kind of acknowledge or kind of look at this one and then kind of look at this one and like, wait, those numbers look all familiar. Like, yep, but they're reversed. They're in the wrong spots, right? That's why I did 3 1/3. So if I go ahead and draw my graph here, right, we do 1, 2, 3, 1, 2, 3, 1, 2, 3. Oops, that's 9, 6, and 3. Okay. All right, so when x was 1, y was 0. Okay. When x is 1/3, y is 1. So we have about 1/3 there, up here. We need 1/3 of 1/3, that's 1/9. Okay. Up here too. When x is 3, y was, right? When x is 3, y is -1. Okay. And when x was 9, that we are at -2. Okay, and I do. This is one of the other. This is one of the advantages of your books. I remember my books that did this spent a very long time on the chapter that talked about bases that were not, arbitrary bases. Your book has a couple of problems, and then they move on and do something else, and they don't belabor this point and make it seem like you're really going to need to know this. Like, no, you're really not. Okay. So it's nice to have it. Like I said, I will ask you a question on graphing them because, it's a function and we do math and it's one of those. So I will ask you a question that looks like one of these three that we did on your exams to like graph it for me. And that's why I try to break it down with the steps. I'm like, okay, we're going to do this, we're going to do this, we're going to do this. Okay, so it won't be a nice one. It'll be like a 1/3 or a 1/5, right? 4/5 or something terrible. But we'll definitely review this when we get there. Okay, but you'll notice, like, hey, wait a minute. This is like, log of like 1/b of x, right, was equal to negative log b of x. And yeah, that's a thing because this is b to the -1 and it comes out over here. Okay, so that's an easier way to think about this. Although to tell you the truth, it comes up so rarely. It's not worth committing this to memory or kind of saying this is a thing you really need to know. We really need to know, and there are 3 things we really need to know. Okay, now I'm going to go ahead and start an example with the 3 things that we need to know. So I am going to ask us, we're going to go ahead, these are all going to be log base 10. Okay, these are all going to be log base 10, which is this button on our calculators. Okay, so we are not dealing with any weird bases. This is just going to be log base 10. This will work for any base, but when we first start, I just really want you to get a sense of the numbers rather than trying to figure out like what all the bases are. Okay, I want this to be a calculator exercise so you kind of get used to it. So I'd really like us to figure out, okay, what is the log of, say, 18? And then I'd like us to know what is log of 3 plus log of 6? What is log of 2 plus log of 9? Okay, so we'll do log of, turn it on. We'll do log of 2. That was 0.301. We'll go 4 decimal places because all the CRC books went to 4 decimal places. Plus log 9. And it was 0.9542. 0.9542. Okay. And this is log 3. So 0.477, I think 1. And then we have log of 6. Okay, and this was 0.7782. Okay, and log of 18. Okay, so that was log of 18. And this is 1.255. So we're just going to add these together. We're going to compare them to 3 decimal places. Okay, because I know that 4 is going to be kind of weird. But we're going to say 0.3001, 3010, plus 0.9542. 1.255. Oh, that's an interesting coincidence. It's not a coincidence. So 0.4771 plus what was that, 7782? 1.25. Hey, wait a minute. These are all the same. So I'm going to ask you, like, well, how do 18, 3, and 6, and 2, and 9? Like, what is the relationship between this pair, and this number? And I know I'm belaboring the point, okay? But the idea here is that the log, this is how you're going to see it. This is any base, by the way, so I'm not going to write the base. Just assume it's all of them. Okay. The log of a times b is equal to the log of a plus the log of b. All right. So we have that. That's a thing. That is really a thing. Okay. So what about let's do how about the log of 6, and we'll do the log of 18 minus the log of 3, and how about the log of 18 minus log of 2? No, that's going to give us 9. I guess we're just stuck with that. Let's see, what other ratios can I come up with? 6. How about the log of 48 minus 8, log of 8? Okay. If you do this in a calculator, okay, you're going to find that 18 and 3, 48 and 8, these all have something in common as well, right? Wait a minute. Yep. 18 over 3 is 6. 48 over 8 is 6. So the function that we're going to come up with here, okay, is going to be log of a over b is equal to the log of a minus log of b. All right. I rushed it a little bit. Okay. Last one. Log of, how about we do the log of 81? And we do 4 times the log of 3 and 2 times the log of 9. All right. So if we go ahead, I'm just going to do them all in the calculator. I'll say log of 81. Oops, 81. 1.908. Okay. Log of 3, or log 4 times log of 3 rather. Okay, 1.908. This is looking a little suspicious here. Pick up to something. Hey, wait a minute. These are all the same. So again, like we have 81, we have 2 and 9, and we have 4 and 3. So how do these all relate? You might say, well, 9 squared, you know, 3 to the 4th is offhand. Let's find out. So 3 to the 4th, that must be 81. Who would have thought? And 81, these are all the same number. So Notice that we have the multiplier out in front. So we're going to say log of a to the r is equal to r times log of a. Right? And that is a thing as well. So the three rules that I'm going to leave us with today are going to be log of AB is equal to log of A plus log of B. Log of A over B is equal to log of A over log of B. I'm sorry, why did I write that down twice? Right, minus log of B. And log of A to the R is equal to R times log of A. And those are three rules that we have. Okay? These are rules that you will memorize till the end of time. Okay, so when Alzheimer's disease rips away every memory you have, you will still have these three rules in your head. Okay, that's how important they are. So you can lose your family, but you won't lose your three logs. Okay. So notice that you do not have, like I didn't say anything about that. And I didn't say anything about this. These are not things. These do not have rules. If you have like a log of like x plus 1, then you've got log of x plus 1. You're done. That's all you have. So don't think that we're going to separate these out because you can't do it. All right. So if you have something like this, log of a plus or minus something, well, there is no simplifying that. You're just stuck with it. Okay. So, but those are our three logarithm rules. I'll give you a couple more. Log base b of b is equal to 1, right? So what power do we have to raise b to in order to get to b? Right? Log raised what equals b? The answer, of course, is always 1. Okay. I usually don't remember this law explicitly because I'll often do something like log of 10 raised to the third power is equal to 3 times log 10. And then now I'll go ahead and call that 1. Okay, but I don't usually just go with the second rule. Right, that's our second rule. I usually make this 2 steps because I remember this rule really well. And then this rule not quite so much. I mean, I know it, but you know, I don't think that way. I think this way. This one is important because it's not the usual kind of way you're going to think about this. All right. So what this is saying is that when we have variables in the exponent position, we're going to use a logarithm to get them down on the ground again. Okay. When we have variables inside of a logarithm, we're going to make each side a base and raise it so we have an exponent of the log, and then be able to do that. So what if I said we have 3? Oh no, I want to do 10 because that's what we have. We can check it in the calculator. Okay, so we have 10 raised to log, the same one in your calculator, log base 4. Okay, and what is that going to be? So we have 10 raised to log, we'll say 4. Okay, we can even do this in 2 pieces. Okay, so you can say, well, what's log 4? Like, are you kidding me? Okay, so that looks like a terrible number. So log 10 raised to, that answer, back to 4 again. Okay, so 10 raised to the log of anything, is that anything? Okay, so we're going to use this to undo logarithms. So I'm going to ask you a lot of times, like, how do we get the variable out of a log? Well, it's called taking the anti-log. That's a boring word. I use unlogify, but that's a word I made up, so don't say that to people because they'll look at you like, what? But that's what we're doing. Is we're making each side a base. We're making each side the exponent to a common base. Okay. So when we get there, we're solving equations. You'll see we're going to use this a little bit more. Okay, but for now, right, these are the three that you have to know for all time. Okay, I'm going to go ahead and stop there, and we'll pick this up tomorrow. We'll keep doing logarithms, but I think we'll have enough time for you to get bored of these and say these were too easy. And at least that's my hope. So I'll go ahead and stop here.